So today we have two related topics. The first of which is the concept of source transformation. So source transformation relies on the concept of electrical equivalence, which is something that we've been talking about this entire time. We just haven't really given it a name. So what I mean by electrical equivalence is, let's say that we have a network 1, and it contains a voltage source Vs connected to a network that contains, let's say, a resistor R1 like so, a resistor R2 like so, and a resistor R3 like so. This is electrically equivalent to a network containing that same voltage source Vs connected to a single resistor Req, where Req is R1 times R2 plus R3 divided by R1 plus R2 plus R3. And we can actually measure these networks' electrical equivalence by observing a voltage VL, what I'm going to call a load voltage, across our network, and a current IL flowing into our network. So let's call this VL1, VL2, IL1, IL2. And we can say that VL1 is exactly equal to VL2 and IL1 is exactly equal to IL2 when our equivalent resistance Req is R1 times R2 plus R3 over R1 plus R2 plus R3. Okay. So we could manipulate further resistors. We could have a network that combines multiple sources and still have this same definition for electrical equivalence, where our load voltage and load current have to be the same between our original network and whatever our simplification is, okay? So what we are going to do today is show that under certain conditions, this network, where I have a voltage source in series with a resistor RS, which I'm going to call from here on out a practical voltage source, is, under certain conditions, electrically equivalent to this network, where I have a current source IS in parallel with a resistor RS, which I will, moving forward, refer to as a practical current source. So what we are going to do here, actually, before we even do that, I want to point out one thing that's very important here. The value of the resistor RS in both cases must be the same, okay? So the RS and the practical voltage source, let's say that it were 5 ohm resistor, the RS and the electrically equivalent practical current source would also have to be a 5 ohm resistor, okay? So let's talk about why we call these guys practical voltage sources and practical current sources for just a moment here, okay? So if I had an ideal voltage source, what's the maximum amount of current that it could carry? The voltage source. So if I have a voltage source, an ideal voltage source, like so, right? And I connect my ideal voltage source to a resistor. This is my current that is being provided by my voltage source, right? We could use Ohm's law to easily say that our current I is simply 5 volts divided by the resistor value. So what if my resistor is a short circuit? So the limit of I as R goes to 0 is infinity. Can a real voltage source supply an infinite amount of current? Well, of course not, okay? So what this simple resistor here, RS, does is limits the amount of current that could ever be supplied by this source. If we had connected a short circuit across the terminals of our practical voltage source, the maximum amount of current, known as our short circuit current, would simply be Vs divided by Rs, right? It is bounded to a finite value. So it is more representative of what an actual physical voltage source, like a battery or something like that, would behave. They have internal resistances, typically on the order of a few milliohms. But we know that an actual physical battery obviously cannot supply an infinite amount of current. And we model that by putting that resistor RS in series with our practical, or with our ideal voltage source to come up with a practical voltage source. Similarly, we could look at a practical current source. What's the maximum amount of voltage drop that could occur over an ideal current source? Infinitely large, right? But if we place that resistance RS in parallel with an ideal voltage source, now our maximum voltage, known as the open circuit voltage, is simply the product of IS and RS, so that we've bounded the amount of voltage that can be effectively provided by a current source, okay? So now, let's talk about their electrical equivalents. We're going to look at two circuits. Let's say we have a voltage source Vs in series with a resistance Rs, so that we have some practical voltage source connected to an arbitrary load resistance RL. so that we can measure a voltage drop VL and we can measure a current IL. Over here on the right-hand side, let's look at a practical current source. Connected to that same load resistance, RL, so that we can measure a load voltage VL and a load current IL, right? So for our left-hand circuit, we can easily see that our load voltage VL is simply Vs times RL over RS plus RL. And on the right-hand side, our load voltage VL would be IS multiplied by RS times RL over RS plus RL. So on the left-hand side, I'm just using voltage division to get my voltage drop VL. On the right-hand side, I'm using Ohm's law to get my voltage drop VL. And from here, we can do it with the currents in a moment if we feel that we need to. But we can see that under a very specific condition, the voltage drop over our resistor RL will be the same. Can anybody tell me what that condition is? What makes these two things equal? Exactly right. When Vs is equal to Is times Rs, these two practical sources are interchangeable, which allows us to transform a practical voltage source into an electrically equivalent practical current source and vice versa, where effectively we're governed by Ohm's law and the fact that we have to use an identical source resistance in both cases. If we had analyzed the current IL, we would actually get the exact same relationship, okay? So I want us to analyze a circuit. If I can find it. Here we go. So here's our circuit of interest. We have a 5 amp source, a 3 ohm resistor, a 4 ohm resistor, a 7 ohm resistor, a dependent source that is voltage controlled of 3Vx in parallel with a 17 ohm resistor. A 2 ohm resistor, a 9 ohm resistor, and finally over here on the right hand side, a 1 amp source. So how many nodes does this circuit have? 5. How many meshes does this circuit have? 5. Are there any resistor or source combinations that we could employ to simplify this circuit? There aren't any resistors in series. There aren't any resistors in parallel. There aren't any current sources in series, or excuse me, in parallel. There aren't any voltage sources, period. So I would argue that before we introduce the topic of source transformation, a problem like this would be out of bounds on an exam because it is beyond the level of your calculators to handle. What we are going to do is we are going to employ source transformation techniques to simplify this circuit down to something that we could have actually analyzed on the second day of class. Okay. So the first thing I'm going to do is I'm going to identify my practical current sources here. So everything in this red box is a practical current source. Everything in this orange box is a practical current source. And even though there's a dependent source here, because I have a current source in parallel with a resistor, everything in this purple box is also a practical current source. So let's look at the one on the left first. Okay. If I have a 5 amp source in parallel with a 3 ohm resistor, this is electrically equivalent to a voltage source in series with that same 3 ohm resistor, where the value of the voltage source is simply 5 amps times 3 ohms, or 15 volts. Now I want to point something out here, okay? When the direction of our arrow is up, positive polarity terminal of the voltage source will be on top. So effectively, the positive polarity terminal of our voltage source corresponds to the head of the arrow. The negative polarity terminal of the voltage source corresponds to the tail of the arrow, okay? Let's look at our 9 ohm resistor in parallel with a 1 amp source. So that's going to look like a 9 ohm resistor in series with a voltage source. What's the value of the voltage source going to be, Michael? 9 volts. 9 ohms times 1 amp. Gosh, I don't know why my screen is wiggling. Is 9 volts. And finally, let's look at our practical source that contains our dependent source. So here is our 17 ohm resistor. Here is our 3Vx current source, and let me get the direction right here, okay? This is still going to be a 17 ohm resistor. The voltage source should be negative polarity on the left, positive polarity on the right, since the arrow is going from left to right. And the value of this voltage source should be 3Vx times 17, or 51Vx. Okay. So what I'm going to do now is I'm going to take my original circuit. I'm going to do this by making a copy of it. And I want to do this to walk you through exactly how I treat these. So I'm just making a copy. And then down here, what I'm going to do is effectively, I'm going to disconnect each of these networks and replace them with their electrical equivalent. So I'm going to delete this guy over here, my 5 amp source in parallel with my 3 ohm resistor. And I'm going to replace at that same terminal pair with, a 15 volt source in series with that 3 ohm resistor, okay? So effectively, I unplugged that practical current source, converted it into a practical voltage source, and then plugged it right back in. I'm going to do the same thing over here on the right. So I unplugged that practical current source. And now I'm going to plug in the 9 ohm resistor in series with the 9 volt source. And lastly, I need to do it to this guy as well. So here's the terminals where my practical current source was connected. Now I have a 17 ohm resistor in series with a 51Vx voltage source. So we took a 5 mesh circuit and knocked it down to a 2 mesh circuit. All right. But let's look at what those rearrangements did. So previously we didn't have any, oh, and I need to keep this as my voltage Vx, which maybe accidentally. So before, there were no resistor combinations that we could make whatsoever, right? But doing our source transformation on the left-hand side has placed the 3 ohm resistor in series with the 4 ohm resistor. So now I'm going to delete my red box here since we've done our combination. I can see that since 3 is just in series with 4, goodness gracious, I can combine these into a single 7 ohm resistor. Since my 2 ohm source, my 2 ohm resistor is where the voltage Vx is defined, I'm going to leave that alone. But I am going to argue that the 17 ohm resistor and the 9 ohm resistor are in series because they have to be carrying the same current because they're both connected to the same branch and there's no opportunity for any current to branch off. So I can erase the 17 ohm resistor, add it with this 9 ohm resistor, and if I'm not mistaken, 17 and 9 gives me 26 ohms. Now, what I'm going to do after I erase these old boxes defining my practical sources, is I'm going to observe that this 15 volt source in series with a 7 ohm resistor is a practical voltage source. If I were to perform a source transformation here, what would that do? It placed the 7 ohm resistor that's currently in series with the 15 volt source in parallel with that other 7 ohm resistor, allowing me to combine those, right? So what's 15 volts in series with 7 ohms look like? Let's look up here, okay? Our top example on the right-hand side, we have a 15 volt source in series with a 3 ohm resistor. And we're saying that that's electrically equivalent to a 5 amp source in parallel with a 3 ohm resistor. So if I had, instead of a 3 ohm resistor, a 7 ohm resistor, how do I work from the right-hand side to the left-hand side? Exactly right. So it would look like a 15 volt source, a 15 volt source in series with a 7 ohm resistor is going to look like a 15/7 amp source in parallel with a 7 ohm resistor, right? This transformation can go both ways. So to go this way, Vs was simply Is times Rs. To go the other way, Is must be Vs over Rs, which is exactly what Kevin suggested. So I'm going to delete this guy. And replace it with a 7 ohm resistor in parallel with a 15/7 amp source, like so. And as I suggested earlier, we now see that the two 7 ohm resistors are in parallel, so we can combine them. So what do two 7 ohm resistors in parallel look like? 3.5, right? Because it'll be 7 times 7 over 7 plus 7, 49 over 14 is exactly 3.5. So I'm just going to call this 7/2. And now, finally, if I converted this practical current source on the left here back into a practical voltage source, I would have a single loop circuit that we could have analyzed on the second day of class as soon as we learned what Kirchhoff's voltage law was. Kirchhoff's voltage law and Ohm's law are the only things that are needed, right? So to convert this back to a voltage source, I'm simply going to multiply that 15/7 amps current by 7/2 of an ohm, and that should give me a voltage of 15/2. In series with 7/2 ohms, like so, we're left with a single loop circuit. Where, just for the sake of argument, let's go ahead and do the analysis here. Negative 15/2 volts plus 7/2 ohms times I minus 51 Vx plus Vx plus 26 ohms times I plus 9 volts is equal to 0, where I'm saying I is just this current flowing around the loop. Ohm's law tells us that Vx is simply 2 ohms times I. So negative 51 Vx plus Vx looks like minus 50 Vx. Minus 50 Vx is going to be minus 50 times 2 ohms times I. I now have it in terms of a single variable. So I'm just going to throw this into my numerical solver, where I have negative 7.5 plus 3.5 x minus 100x plus 26x plus 9 is equal to 0. Solve for x. Waiting on my calculator to give me a result. Surprised at how long this is taking for the simple linear equation. Says I typed something in wrong. Negative 7.5. Oh, there's we go. I got I to be negative 76.923 milliamps, which in turn would tell us that Vx is simply 2 times that, or negative 153.846 millivolts. So the analysis here at the end should have been fairly trivial because we've been doing it for the better part of 2 weeks right now. What I'm trying to show you guys is how we can use this concept of source transformations to make a really ugly looking circuit something much more manageable, right? Okay. Our next topic is the concept of, why is this? There we go. Maximum power transfer. So let's look at a practical voltage source first. Here is Vs. Here is Rs. Here is RL. Here is IL, okay? So what's the power delivered to that load resistor RL? Not supposed to be a trick question. VL times IL. The voltage drop over the load resistor multiplied by the current flowing through the load resistor, because power is always voltage times current, right? So PL is equal to VL times IL. I'm going to express the quantity VL in terms of our voltage Vs here by using voltage division, much like I did earlier. So I can say that that is going to be Vs times RL over Rs plus RL. And I'm going to express the current IL using Ohm's law and say that IL is simply Vs divided by Rs plus RL. And from this, we can observe that the power absorbed by our load resistor, PL, is simply Vs squared times RL divided by Rs plus RL quantity squared. Are we okay with this? If I were to plot PL as a function of RL, so let's put PL on this axis and RL on this axis, and I'm just going to let RL range from 0 to infinity effectively. What I would observe is a curve that looks something like this. Where the vertex of this graph corresponds to the value of RL that makes the practical voltage source deliver the most amount of power. So I'm going to call that P max. Okay. So on this end of the spectrum, we have RL is equal to 0, indicating that our load resistance is a short circuit. We know that there should be no power delivered to a short circuit because the voltage drop across a short circuit is 0. And so 0 squared over 0 looks like 0. On this end of the spectrum, we have an infinitely large resistance where we know that we should have no power absorbed because there's no current flowing through the open circuit, right? And so 0 squared is obviously going to give us a power of 0. All points in between represent any possible resistance that we could connect to this thing, okay? Ranging from 0 all the way out to infinity. And we can see that for most points, or for most power levels, there are exactly 2 resistors that give us that, right? So if I were to draw a line like so, just for the sake of argument, and say that this was 3 watts, we could see that there's some small resistor value that when connected to this thing would make our circuit output 3 watts. And there would be some very large resistor when connected to this practical source that would also correspond to it delivering a power of 3 watts. Our maximum power is the only point on our shape here that has a single value for the resistor that will satisfy that constraint. And as it turns out, that occurs when RL is exactly equal to RS, our source resistance. Okay. That result, for those of you who want to suffer through the math, is obtained simply by taking the derivative of our PL relationship with respect to RL and setting it equal to 0, because that's how you find the maximum value of any function. Right? So in the instance where RL is exactly equal to RS, our maximum power is Vs squared times Rs over twice Rs squared, which becomes 1/4 Vs squared over Rs. So this tells us the maximum amount of power that any practical voltage source can deliver to a well-chosen load resistance. We could go through a similar derivation for a practical current source, but it's really not necessary because we know that an electrically equivalent practical current source would occur when Vs is equal to Is times Rs. So for a practical current source, here we have Is in parallel with Rs. Here is VL. Here's our load resistor, RL, our current IL. Maximum power transfer, again, will occur when RL is exactly equal to RS. And our equation is simply 1/4 Is squared times Rs. All right, so our last example for the day before I stop talking and boring you guys. Whatever they're listening to in the next room is absurdly loud, in my opinion, is the following circuit. All right. So I'm going to break this circuit down into two questions. Question number one. What value, I can't spell this morning apparently, of RL will cause the remainder of the circuit to deliver the most power and question number two is what is the maximum amount of power that RL can absorb. This is literally identical to how I'm going to ask you questions on this topic on your exam that's coming up next Monday. You're going to have exactly two problems, one of which will involve calculating the value of RL, where maximum power transfer will occur. And the second part is then telling me what that maximum power is. Okay. So when we did our maximum power transfer stuff a moment ago, we did that in terms of a practical voltage source or a practical current source. So our first step in this problem is to reduce everything that isn't the resistance RL down to either a practical voltage source representation or a practical current source representation. So how are we going to do that? Victoria, do you have any thoughts? Absolutely right. So Victoria has identified that we have a practical voltage source formed by the 12 volt ideal voltage source in series with the 3 ohm resistor. What is the practical current source that is electrically equivalent to that? 4 amps in parallel with 3 ohms. So what I'm going to do, I'm going to put a pair of terminals here. I'm going to erase this guy. And I'm going to replace at those terminals with my electrically equivalent source, which was a 3 ohm resistor in parallel with a 4 amp source. Are we all in agreement that that's what our electrically equivalent circuit should look like after this first step here? All right. So what can I do to simplify things now? Seth. All right. So the equivalent, excuse me, the 3 ohm resistor and the 6 ohm resistor are now in parallel. So we can replace them with a single equivalent resistance. So that would be 3 times 6 over 3 plus 6, or 18 over 9 is 2 ohms. What can I do now? Go back to a practical voltage source. Okay, so how would I do that? All right, so 8 volts in series with a 2 ohm resistor. I agree with that. What can I do now? Devaria. All right, so 2 in series with 7 is 9, right? And now I have a practical voltage source connected to my load resistance, RL. So how do I answer question 1? RL must be equal to what in order for maximum power transfer to occur? 9 ohms. Eric, how do I answer question 2? What's the maximum amount of power that can be delivered? Why would we use the equation for a practical current source when we have a practical voltage source? So use the other one, the one with the VS. Yeah. So 1/4 VS squared over RS. Well, that's 1/4 times 8 volts squared over 9 ohms. Looks like 64 over 36 watts, and I'm going to be lazy and not simplify that. That's the answer to part 2. That relative level of difficulty is actually what you should expect on your exam as well. And if you look at the practice test, you'll see that's kind of what we're going for. All right, so any questions regarding the concept of source combinations or, source transformations or maximum power transfer?